make defects in space-time, things like that. So along those directions where orientable plane is in some point, translational invariant should be broken.
Transverse direction. In a transverse direction, yes.
Yeah.
Yeah. Because once you have an orientifold, you have already chosen a preferred point, right? The fixed points, yeah, the preferred points in that plane. So translation invariant certainly will be broken.
One more thing, so these things are charged under other fields. So is any easy way to see that these things should source other fields, orientifold planes?
Yeah, it's done exactly in the same way that you show for D branes. Right? The fact that D branes carry RR charge, right? What I want to show is that you use this open closed string duality, right? You look at the open string partition function, look at the open string partition function on one channel, but that can be reinterpreted as a closed string exchange with RR diagrams. So it's the same thing here for orientifold planes, right? You use a similar diagram, except that instead of open strings, you have closed strings with a projection operator, right? Which are called the cross caps. And again, you see that if you have two cross caps, for example, right, they have the partition function, the modification of the partition function due to the projection, right, which is captured by the cross cap, can also be interpreted in the cross channel, okay, which is the exchange of RR fields. So it's basically similar to what you do for D branes, okay, except that instead of open strings, you use closed strings, but not the oriented part of the closed string. It's the extra term that you get from the projection. Inserting the projection operator.
These planes are not dynamical, so although they source other fields, I mean, if I turn on some other field due to some other D brane also, these things will not feel any force.
Well, it depends on what you mean by they will not feel any force. Right? Eventually, you have to. I mean, they don't have a translation mode in the transverse direction. If that's what you mean by dynamical, yeah. But the feeling of force, right? I mean, all the fields have to satisfy the equations of motion. Okay? So if the orientifolds have some degrees of freedom living on them, right? They are no massless degrees of freedom because you can't move them. Okay? But if there are some massive degrees of freedom, for example, they have to satisfy their equations of motion. Yeah? There can be massive degrees of freedom. I mean, these massive degrees of freedom, and again, you can think of this as a closed strings which are going around the orientifold plane, right? That you can think of as something associated with the orientifold plane, right? It's regular closed strings, okay? Except that these closed strings appear only because the orientifold plane you have made an extra identification, right? For example, in the orientifold plane, you identify a point here with a point here, right? If this is a fixed point, okay? So a string which was not closed before is now closed, right? So these strings are in some sense localized on the orientifold plane because if you try to take them far away, right, the length increases, right? It costs energy to move them far away, right? So you can naturally think of this as these strings are really localized near orientifold plane. Okay. And these you can think of as the dynamical degrees of freedom of the orientifold plane. And their equations of course also have to be satisfied. Okay. But they are typically massive strings.
So one can write down world volume action for.
Yeah, world volume action for these fields is the same. Locally world volume action is the same, right? It's just the global identification, right? That these strings have the property that when sigma goes to sigma plus 2 pi, right, x goes to minus x, if x is this coordinate. Right? With that boundary condition, you quantize these strings. Okay, you get certain number of states of the string, and those states you can think of as being associated with orientifold plane. Right? Just like twisted sector states in normal order. Yes.
Can you explain once again the monodromy around O7 plane?
Monodromy around O7 plane? Okay. So the point is, around the O7 plane, we had earlier seen that there is a monodromy of -1, -1, right? Because you define the O7 plane by modding out by -1 to the f left times omega, right? Okay. So as you go once around the O7 plane, you have to make this transformation, right? And that is equivalent to -1, -1 of S to Z. Okay. But on top of that, you saw that O7 planes carry RR charge, right? So C0 goes to C0 minus 4. Why minus 4? Because it carries -4 units of RR charge. Okay. So C0 goes to C0 minus 4 as you go around the O7 plane, right? That corresponds to tau goes to tau minus 4. So this is represented by a monodromy matrix which is 1 minus 4 0 1. Okay, and the monodromy, total monodromy around 0710 you are getting by multiplying this one, right, which was there even to begin with, right, with this one. Okay. Well, if you consider a configuration that SO8 to the 4 configuration where 4 d-branes are on top of the orientifold planes, right, then what happens is that this gets cancelled by the corresponding monodromy of the 4 d7 planes, which is fourth part of this, right, 4 d7 planes. So this product is identity. Okay. But even in that case, there is a leftover monodromy which is this one. Right. So you take the monodromy of the orientifold plane as minus 1 4 0 minus 1, right, which is nothing but this multiplied by minus 1 minus 1. And this times the fourth part of this gives you back minus 1 minus 1. Is this okay? And
that factor won't be there for the D7 monodromy.
This factor. Yeah, this factor will not be there for a D7 monodromy, because as you go down the D7 brane, right, there is no minus 1 to the F left times omega transformation, right? D7 branes only carry pure Raman charge, and that's what happens. Okay, any other question? Okay, so let me begin by giving you some clarifications. So the first clarification was about the action dilaton equation. Okay, this is related to I think one question that Anirban had asked earlier. Okay. So let's derive the action dilaton equation from scratch and see what you get. So the action for the action dilaton term is proportional to basically square root of determinant G tilde. So this is the internal 6-dimensional metric, the what part of this metric. Okay, this is the action for the action dilaton part. Now, the reason that I am using the Ward metric, okay, this G tilde, you remember the G tilde was related to G mu nu by scaling, right? Is G tilde mu nu times e to the 2f probably, but this is Mn. And G mu nu was e to the minus 2a times eta mu. Okay, I don't remember the sign, it's plus a for one, minus a for the other one. So the reason that I have written the action in terms of this, right? I mean, I should have written it as determinant of G. Okay. But then I have to also include both the 6-dimensional metric and the 4-dimensional metric. Okay. The 4-dimensional metric gives you a factor of e to the minus 4a. And the idea is that e to the minus 4a gets cancelled if you use G tilde. Okay. So square root of determinant G or minus determinant G6, sorry, square root of minus determinant G4 times Gmn. This is the same as square root of determinant G tilde 6 times G tilde n. Okay, that's the reason I am writing it in this form, otherwise I could have written it in terms of G, okay, which is of course the original metric. But then you have to keep also this factor, okay, because this determinant is not 1 but it's just e to the 4a or e to the minus 4a from here.
You mean G tilde mu nu here in the last two lines?
G tilde mn, sorry, this is mn and this is the 6 dimension. Okay, so then let's start with this action and try to derive the equations of motion. So equation of motion we can derive by varying tau bar. Okay, I could have also done it for delta tau, it will just give the complex conjugate of the equation of motion. So if you vary tau bar, okay, delta S becomes integral square root of determinant G tilde there are two terms now. One is del m tau bar, del n delta tau bar, tau minus tau bar square, plus 2 g tilde mn Okay. See, this came because you are varying the tau bar from here. The second term came because there is a tau bar sitting here, that also you have to vary. Okay, that's this term. So now we can integrate by parts. Okay. So this one by integration by parts becomes minus del tilde m del tilde m and now delta tau bar just factors out. Okay, basically I have taken the derivative from delta tau bar and put it on the rest, okay, which is 1 over tau minus tau bar square times del m tau. Okay, this is the ordinary derivative, okay, but this is covariant because this has to basically act also on the determinant. Is this okay? So to get the equation of motion, you basically have to set it equal to 0. Okay. So let's calculate this side. So this side has two terms. One is minus 1 over tau minus tau bar square. But then there is a term where this acts on this one.
This g tilde m is in the second term in delta S.
Yes.
We have already taken out the g tilde m.
I have here.
In the second
yeah,
term.
yeah.
Yes.
Okay. Yeah, so g is tilde m.
Below also.
No, below I have put that g tilde m and back. See this, because this now have contracted it.
Okay.
Del tilde m, right? Otherwise I will have to write it as m and n. That also I can do. Okay, then below also I can do this. So this will now be del tilde m. Okay, so when we evaluate this, okay, the first term there is a both derivatives act on tau. Okay, that's this term that I have written here. So there is a minus sign, so let me write that minus sign. The second term is when this one acts on this. So that will be g tilde mn. Now it will be 2 over tau minus tau bar cube del tilde m tau minus del tilde m tau bar times del tilde m tau, and then the last term plus 2 over tau minus tau bar cube. But this I can write also as ordinary derivative. this should be 0. That's the equation of motion. Okay, these also, or I can just replace with ordinary derivatives. Because acting on a scalar, covariant derivative and ordinary derivative are the same. So del m. This is there. In any case, now the point is that this term, because of this minus sign, this exactly cancels this term. Okay, so this term and this term goes away. And now we are left with an equation. Now tau minus tau bar square you can multiply by, so is this okay? So this is, both are tau. Okay, that's going to be important. Both are tau. Okay. So first of all, okay, last time we said that we will take tau to be large. Okay, so that the equation is only this one. Okay, and then a holomorphic tau. Pardon?
Right hand side there should be a GT element, or you should raise the
Yes, it is. Okay. So if tau 2 is large, quick coupling, right? Then of course this is small. Okay, and we can just focus on this. This is telling us that tau has to be harmonic, right? So holomorphic tau certainly satisfies that. Okay. But even if we include this term, okay, we can see that as long as the metric is flat, okay, as long as the metric is flat, holomorphic tau of course will satisfy this, okay, because a holomorphic function is also harmonic, okay. But this one also vanishes identically. Why? Because this is z bar, right? In this coordinate system, you have to take del z bar tau, okay. And if tau is holomorphic, then del z bar tau is 0. Okay, so the holomorphic tau makes this automatically vanish. Okay, so you don't have to take this to be, you don't have to invoke the large tau to approximation here. Okay, but of course you cannot really get rid of the large tau to approximation because you are not in calculating back reaction on the metric. Okay, is this okay? Okay, the other thing I wanted to point out is some convention about the coordinate system, but didn't specify in detail. So yesterday we took the metric to be flat, right, like this. But in actual practice, the metric is not really flat in the z coordinate system. Okay, so let me try to explain this point. So the way we describe the orient before is that you started with the torus, and then we made an identification of diametrically opposite points. Okay, so the metric can certainly be written as a flat metric in the torus coordinate system. Okay, because on the torus coordinate system, if tau is a modular parameter, well, this is a different tau, so let me call it sigma. Okay, sigma is the modular parameter of the torus. Then you can just define W as x8 plus sigma x9, and then in this coordinate system ds square is mod W square. mod dw square. Right? This is, so in the w coordinate system it's clearly a flat metric. Okay, this is how you write a torus in terms of a flat diagonal metric. Okay, but the identification is slightly different for w. So w, for example, is identified as w plus 2 pi and also w plus 2 pi sigma. Okay, this is what we normally call tau, but now that we have different tau, I am calling it sigma. Okay, but the orienting fold that we are considering is obtained by identifying w with minus w. Right? So we identify w with minus w, which basically means that if you are working close to the point w equal to 0, then w is not really the good coordinate system. Right? Why isn't it a good coordinate system? Because w and minus w actually describe the same point. Right? So a good coordinate system will be the one where a coordinate, at least in the local neighborhood, specifies a point uniquely. Right? Different values of z should represent different points. So the correct coordinate system near w equal to 0 is actually w, which is w square. Is the correct coordinate. Okay. So the flat metric on the torus actually becomes, so dw square becomes proportional to up to factors of 1/4, etc. We can see that w is z to the half. So dw is half dz over z to the half. So this becomes basically dz mod square over z to the half. Okay, it is still flat metric because after all changing coordinates doesn't make the metric non-flat, right? It's still flat metric except that there is a curvature, there is a concentric curvature at z equal to 0. Okay, away from z equal to 0, okay, you can change coordinates and write the metric as dw mod square and it's flat. Okay. And when we say tau is holomorphic, right, strictly speaking, at least it's easiest to see that holomorphic tau satisfies this equation in the w coordinate system. Right? Because in the w coordinate system, the metric is really mod dw square. Right? So if tau is holomorphic, then clearly both terms vanish independently. But a function that is holomorphic in w, okay, once you write in terms of z, is also going to be holomorphic, right? Except for certain singularities. Okay, so even in z coordinate system, tau should be holomorphic, okay, away from the singular points. So we can also actually write down the correct metric on the full tetrahedron. Okay. So the full metric on the tetrahedron is actually this: I equal to 1 to 4 dz mod square over okay, so that wi's are the locations of the orienting fold lengths. Okay, so there is, so this example that I considered was when say one of the w1 is 0, okay, that's why mod dz square over z to the half, z bar to the half. But if you want to know the full metric on the full orientifold, on the full tetrahedron, it is this one.
Now one should not think of Z as W square. On the
Near the
yeah, near
that point Z is W square, but not in general. Yes. And you can see that this
This is without the difference.
This is without the difference, yeah. This is basically when all the difference are on top of the orientifold planes. Okay? So that you only have the effect of the orientifolding, right? No localized sources, no other localized sources. So in particular, you can see that as z goes to infinity, this metric becomes dz square, dz mod dz square over z square, z bar square. Okay? So if you make the standard change of coordinates, the z equal to 1 over y, right? Y is the good coordinate system near z equal to infinity, then this just becomes dy.
One question. So the singularity at the w equal to 0,
Yes.
that is apart from the singularities of the modular parameter at 2 points.
Of the modular parameter
In
and
the
two.
fundamental region there are 2 points where it's singular, right?
Yeah, so that, let's see.
So there is I think e to the power
Well,
I pi by 6 and e to the power I pi by 4.
those are not really singular points. Right? The torus is perfectly regular at these points, right? In the modular space, there is an extra identification, okay? But it's not that something goes wrong with the torus at these points. Okay? So here, in fact, I mean this whole picture, orientifold picture that I had first, right? When the difference were on top of the orientifold planes, tau is just constant. Right? So tau is not changing at all on the torus. You just set it to any constant that you like, because there are no localized sources. A constant is a valid solution. And with that constant, now you are only talking about the metric, right? And the metric is given by this.
What do you mean by Z equals to infinity? Z should take care in a finite range.
Oh no, but what is Z is supposed to be the coordinate on the sphere, right? So this, you are now think of this as a coordinate on the sphere, okay, on the plane.
Okay.
So this is I am now writing on the exact metric on the tetrahedron. Okay, think of it as a plane. Okay, but plane we know is equivalent to a sphere, at least topologically, once you identify the points at infinity. Okay. What this is saying is that at infinity, the point at infinity, okay, near the point at infinity, you can make a change of coordinates x to 1 over y, and it becomes mod dy square, the metric. Okay. So infinity is actually a finite distance away, right? Because in the y coordinate system, y equal to 0 is a finite distance from y equal to 1. So this is a compact space. Okay, so the fact that we identify the point, see, as far as the topology is concerned, right, you can always identify the points at infinity. Okay? But the question is it true also geometrically? Right? That depends on the choice of the metric. Right? If you want to think of this really as a sphere, okay, geometrically, then it better be that the point at infinity is not infinite distance away. Correct? It's a finite distance away. And what this is showing is that that the point of at infinity is at a finite distance away, because in the y coordinate system you can clearly see that the distance between y equal to 0 and y equal to 1, right, which is z equal to 1, is finite. Okay. So this really describes a compact space now, okay, with the topology of a sphere, where the point of infinity has been identified. And in this compact space there are 4 points where all the curvature is concentrated. Okay. Because away from these 4 points, the metric is the square of a holomorphic function. Okay. dz mod square, okay, divided by holomorphic function times an anti-holomorphic function. So the curvature is identically 0. Right? So the point is that if you have f of z bar, dz bar, a metric of this kind has 0 curvature. Right? Simpler to see that you just redefine fz dz as dw, okay, and it becomes mod dw square. So this has 0 curvature, okay, even though you have not written it as mod dw square. Okay. So all the curvature is concentrated really at the singular points. There are 4 of these. And those are the 4 corners of the tetrahedron. Okay, where the oriented plane is. Okay, so you can so this whole tetrahedron, we can think of course, geometrically you can see what a tetrahedron is. Okay. But you can also write explicitly what the metric is on the tetrahedron by thinking of the tetrahedron as a sphere. And in this form, the point at infinity has been brought at a finite distance away, and there are only 4 singular points at W1, W2, W3 and W4. And the point that I was trying to emphasize is that from whatever analysis I had done, tau should be holomorphic in W because that sort of satisfies the equation of motion. But holomorphicity in W also implies holomorphicity in Z. Okay, where Z is this coordinate system over here. Okay, because Z is really a holomorphic function of W, right? So locally, if you want to write it as dW mod square, you can always do this, right? You can always solve this equation locally, where fz is equal to dW. Okay, and in W it's holomorphic, so in Z also it's holomorphic. So the solution that I wrote down yesterday was in the Z coordinate system. So let me write it again. The solution for tau Z, which is 1 over 2 pi I, so these are the D7 and these are the O7 locations. So this solution is in the Z coordinate system. Plus tau naught also.
If there were not 4 such points,
Yes.
from any such point, 1 or 2, the structure will still be same.
But then it cannot be a half, because if you want to think of this as a sphere, right, as it goes to infinity,
Yes,
it should go as 1 over z square, 1 over z bar square.
yes, that does not work out
Yeah, so you have to change the powers.
accordingly.
Yeah, so if you want to distribute the curvature on the sphere, right, at more than 4 points, you can do that. Okay, but then of course the curvature at individual points should be less, right? So you have to change the power over here.
But if I look from this, I mean, the way we introduce z coordinate near some singularity,
Yes.
that argument still remains the same, that it should be z square.
Yes. So if you do it by orbifolding, right? Then there are 4 singular points. Right? You constructed this by orbifolding a T2, right? So there are only 4 singular points. So you have to distribute the whole curvature at the 4 points only. Right? But you could forget about orbifolds and everything else, right? Suppose you have a sphere, okay, and you want to smoothen out the sphere, distributing the curvature at various points. Okay. Then the metric locally on the sphere should look like mod dz square over some holomorphic function times an anti-holomorphic function. Right? But those functions should have some singularities, because some concentrated curvature should be there somewhere, right? Okay, and those singularities will be of this kind, some with various powers of this z minus zi and z bar minus ni bars. Okay. The condition that they have to satisfy is that as z goes to infinity, this should fall off as this. Okay. Otherwise, there will be curvature concentrated also at z equal to infinity.
So if this is not 4, the orbifolding would also be different.
Well, it may not even be orbifold. I mean, not every sphere of this type can be obtained by orbifolding. Okay. See, these questions can be asked completely generally, without worrying about whether it's coming from orbifold or not. Right? Orbifold of a torus, of course, will always give metric which is flat in most places, right, except at the fixed points. but start with a sphere, right? And you can start smoothing it out, right? Putting all the curvatures at some isolated points. Okay? And then you can ask what will be the metric on such a sphere. It need not be that that particular space has to come from orbifold or something. Is this okay? Okay, are there any other questions? Okay, so the reason that you have that we know that this is the z coordinate system is because if we really use the w coordinate system on the torus, right, then there should really be 32 deviants instead of 16 deviants, right? Because in the w coordinate system you have both the deviants and the images, right? Because that's the double cover. Okay, so there should be 32 deviants. So you could try to go back to the w coordinate system. You have to write a sum over 32 points here, and the charges will also double. Right? So that's how we will count. Because z minus wi will be more like some w square, right? So that 2 will make this 4 into an 8. But we will write it in the z coordinate system. Okay, and let me emphasize again that holomorphicity in z coordinate system, okay, guarantees holomorphicity in w coordinate system, and that shows that it still satisfies equations of motion.
So one more thing, can you blow up this space? Can you blow up this space?
Well, the point is that in this case, it's not like orbifolds, right? In orientifolds, you cannot blow up in the standard fashion. Okay. So here the analog of the blow up, right, the deformations that you can have are this pulling these deviant side from the orbifold plane. Okay, then if we just take a orientifold, right, the natural configuration that you get is when all the deviants are on top of the orientifold plane, right, so there are no localized forces anywhere. Okay. And then you can deform it, but that deformation here corresponds to pulling the deviant side from the orientifold plane, which is what gives rise to this kind of geometry anyway. Okay, but you know that this is not completely correct because as z goes to wi, you have seen that tau goes to minus I infinity, right? And that's clearly nonsensical. Okay, and we'll see how to correct it. Before I go on to the next subject, let me also mention that this procedure of orientifolding, okay, can be generalized to arbitrary manifolds, okay, with respect to symmetry. So generalization. Suppose we have some manifold M which is Z2 symmetric. Fixed points are actually fixed planes with two transverse directions. Okay, what this means that if you are considering a 6-dimensional manifold, okay, then its fixed points are actually fixed 4 planes inside the manifold. Okay, 2 transverse directions. Okay, the rest are tangential to the plane. So near a fixed plane, what we have is we have transverse complex coordinate. Well, let's assume that it's a complex manifold. Okay, in fact, we'll be using it mostly in the context of Calabi-Yau. Okay, because of the reason that we don't want to break supersymmetry all the way from the beginning. Okay. So you want to keep keep supersymmetry at least at this stage. So you will start with the Calabi-Yau and then try to take this ODE4. So you have transverse complex coordinate W and tangential complex coordinate which you can call W1 and W2. Okay. And then the Z2 acts as W goes to minus W and W1 and W2 goes to W1, W2. Okay, that's the reason why it's a fixed coordinate, right? W1 and W2 coordinates, the tangential coordinates don't change. Right? The transverse coordinates change, right? If you go a little bit away in the transverse direction, it comes to minus itself.
When you consider two tangential coordinates?
If it's 6 dimensional. If the total manifold is 6 dimensional, right? Otherwise it will be more. Okay, n minus 2. So the number of such things is n minus 1 if n is a complex dimension of n. Is this okay? So now then we can mod out by minus 1 to the f left times omega times this geometric Z2. And then the fixed planes will become orientifold planes, orientifold 7 planes. Why 7 planes? Because it has only 2 transverse directions. Right? All the rest of the directions on inside the manifold are tangential, and of course the 3 plus 1 dimensional space time is always tangential because the Z2 is not active in those directions.
What does it mean, geometric Z?
This is geometric Z2 is this one, right? Which is acting geometrically on the internal space. Okay, so we combine that transformation with minus 1 to the f left times omega, right? Just like so, this geometric Z2 is analog of the I2, what I call I2 for the torus. Is this okay? Now, of course, you could say why minus 1 to the f left times omega? Why not just mod out by the Z2, right? Or omega times the Z2? Okay, you could do a lot of things. Okay. The reason that you would like to do it minus 1 to the f left times omega is if you want to preserve some supersymmetry. Okay. So, for example, suppose it has a Calabi-Yau threefold. Okay. If it has a Calabi-Yau threefold, then the resulting theory, okay, before orbifolding, before this orientifolding, would have had n equal to 2 supersymmetry. Okay, so let me write it here. If M is CY3, we have n equal to 2 through Z to begin with. Minus 1 to the FL times omega times I2. What it does, first of all, is that these two supersymmetries were coming, one from the left sector, one from the right sector of type 2. Okay? Because the two supersymmetries, the reason that we got n equal to 2 because there were two supersymmetries to begin with, right? It was an n equal to 2 supergravity in 10 dimensions. So one was coming from the left, one was coming from the right. Because it includes an omega, right, it exchanges the two supersymmetries. Okay? So this minus 1 to the f left times omega times I2 first of all exchanges the two supersymmetries. Okay. And on top of that, it picks up some signs of some of the components in general. Okay. For example, -1 to the F left while acting on the right hand left Raman sector, right, will give an extra sign. So you have two supersymmetries which are exchanged, and some of the components may pick up some signs, but it's clear that one linear combination will remain unchanged. Right? If epsilon 1 goes to minus epsilon 2, say suppose epsilon and epsilon 2 are exchanged, right? Then epsilon plus epsilon 2 is invariant. If epsilon is exchanged minus epsilon 2, then epsilon 1 minus epsilon 2 is invariant, and so on. Okay. But you have to make sure, of course, that it doesn't pick up an I. Right? It's an order 2 transformation. If it is an order 4 transformation, for example, then it could have picked up an I. Okay, some of the components. Then it will not help. Right? If A goes to IB, okay, then no combination of A and B is invariant. And this is needed, this fact that we take this combination, this is needed to make sure that it's order 2, that it squares to actually 1 and not to -1. Okay, which could happen sometimes. Okay, if you just have an ordinary rotation in say pi rotation, right? Z to minus Z transformation that you are doing, it's a pi rotation. Okay? Square of a pi rotation is 2 pi rotation. Right? That acts as -1 on the fermions. Right? So the eigenvalues of a pi rotation acting on the fermions are actually plus minus I. Okay, that's the reason we cannot find a covariantly constant spinor if you just include pi rotation. Right? Suppose you had taken omega times I2. Right? Omega will exchange the two supersymmetries, two spinors, right? But I2 has eigenvalues plus minus I acting on the spinors. Okay, so this will not have any invariant supersymmetry. -1 to the F left is necessary to ensure that it squares to 1, okay? And hence its eigenvalues are plus minus 1. Half of them will be plus 1, half of them will be minus 1. Is this point clear? Okay, if it was I4, things should have been different. Right? I4 squares to 1. Okay, there you don't need this -1 to the F left. Right? There, if you include the -1 to the F left, you are in trouble. Okay, you will find that that doesn't square to 1.
So, but -1 to the F left is sensitive to the left sector, right?
Exactly.
But then I2 has eigenvalues plus minus I also has some discrimination.
Yeah, so what happens is that when you square I2, it gives you -1 acting on the fermions. When you square -1 to the F left together with omega, it gives -1. Why? Because first time suppose you have -1 to the F left, right? It changes the sign of the left moving Raman sector, and at the same time it exchanges left and right. Next time you add to this transformation, right? What was left earlier has become right. Now -1 to the F left is not going to act on that, right? So the minus sign remains. Right? And that minus sign is what cancels the square of I2, right? Which also picks up a minus sign acting on the fermions.
And so the order is important. This omega.
No, order is not important. What is important is that you have to act this whole thing once and then again this whole thing again, right? Not, it doesn't matter whether you use omega first or -1 to the F left first, but the same ordering must be maintained. Okay? So that if you have used -1 to the F left, next time you should use omega. Okay? It exchanges, then you apply -1 to the F left, and then there is a confusion. Is this point clear? Okay. So the net upshot is that if we start with a Calabi-Yau manifold, okay, and in that Calabi-Yau manifold, if we can find the Z2, okay, that acts this way, okay, that locally around the fixed planes, okay, it basically changes the sign of one complex coordinate, leaving the other complex coordinates unchanged. Okay, so the fixed planes are actually fixed chord planes. Then modding out by this Z2 accompanied by -1 to the F left times omega preserves half of the supersymmetries, and hence gives rise to an n equal to 1 supersymmetric compactification of type 2B theory. Okay, this is important because this will be our starting point. Then we add fluxes and other things to see if we can break n equal to 1 supersymmetry, lift moduli, and so on.
Can you repeat this part once? So when I add this first time, this vector picks up a minus sign.
Yeah. So first of all, I2 square is -1. That is clear, right? I2 is 2 pi rotation. So square of that is 2 pi rotation. That acts as -1 on the formulas. Okay. Now suppose we apply -1 to the f left times omega. Okay. Begin with a spinner on the right, epsilon r. Okay, and see what happens to it. So omega makes this epsilon L. Okay. -1 to the f left makes it minus epsilon L. Okay, because -1 to the f left will change the sign of all the Raman sector states on the right. Now we apply -1 to the f left times omega again. Okay. Omega makes it minus epsilon r. Minus epsilon r. -1 to the f left keeps it as minus epsilon r. Okay? Because -1 to the f left is supposed to change the sign of the left moving Raman sector. Okay? So net effect is that epsilon r has become minus epsilon r. Right? When you apply this twice. Right? When you apply I2 twice, again epsilon r will become minus epsilon r. Right? Because I2 acts uniformly as -1 on all, I2 square acts uniformly as -1 on all the formulas. Okay? So this whole thing squared will act as +1, okay, which is good because that means that its eigenvalues acting on epsilon must be plus or minus 1. Right? Once you know that it's plus and minus 1, then the fact that it has this off diagonal form, that omega always exchanges, right, guarantees that it half the eigenvalues are +1, half are -1. Okay, are there any questions?
Can you repeat how half of the supersymmetries are
Oh, because if we start with a certain set of supersymmetries coming from epsilon r and epsilon L, right, of them, the plus eigenvalue, the ones which have positive eigenvalue under this will be preserved, right? And what I am saying is that this argument shows that because it squares to 1, its eigenvalues are plus or minus 1. Okay. And then the fact that it has the off diagonal structure, because omega, right, basically takes the left and puts it to the right. Right? So it's the matrix that has the form of 0, A, B, 0, and its square is 1. Okay? Such a matrix has eigenvalues plus or minus 1. And that's what we are using. So half of them are +1, half of them are -1. Because this is traceless, for example, right? This matrix is traceless. Okay? So its eigenvalues better add up to 0. Right? And since the eigenvalues are plus or -1, right? Half of them must be +1, half of them must be -1. Okay? So the ones which have eigenvalues +1 are the ones which are invariant tensors, invariant spinors, right? And those generate the supersymmetries of the final theorem. Is this okay?
So 3/4 of the supersymmetry will be broken because you compactify on the Calabi-Yau, and then on top of that, these many supersymmetries.
Yeah, in fact, not 3/4, 7/8, because once you have compacted on Calabi-Yau, already 3/4 are broken.
Yeah.
Right? And this is, so 3/8 will be broken. Let's say 3/8, no, I'm doing some wrong counting, because eventually, yeah, see, 3/8 are broken, sorry, 3/4 are broken, 1/4 remains. Right? And now after doing this, 1/8 will remain. Right?
Half
So,
of 1/4 will be broken.
yeah, exactly. So basically out of the original one, right, 7/8 are broken. Because we have already removed 3/4 of them, right, and now we are removing 1/8 of them, right? So it's 3/4 plus 1/8 which are being removed.
So from 32 you will get only 4.
Yeah, from 32 you will get only 4, right? That's the n equal to 1 supersymmetric compactification, right? Which is closest to phenomenology, because now you have possibility of getting chiral formulons and various other things, and then eventually you have to know how to break n equal to 1 to n equal to 0. Okay, so now we leave orientifolds for a while, okay, and discuss a different kind of warp compactification. Okay, again, which allows us to construct solutions where tau varies as a function of the internal moduli. Okay, and later on we will make a connection between these two kinds of compactifications. Okay, so that compactification that I will be describing now is what is called F theory. Again, F theory compactification can in principle be done on general manifolds breaking supersymmetry.
So, we started this with a aim that this is like the solutions of tau and G tilde mn will be classified in these two.
Exactly, that's right.
So, what are the implications of solutions for G tilde mn for integral fields?
Oh, for G tilde mn, as I said, the leading order solution, right, has that form, right, and then if you take into account the weak coupling effect, the coupling effects, right, it will have to be modified, right. But it is best to see in this new formulation, right, because you will see the new formulation actually is equivalent to this orientifold, right, and in F theory the metric is easier to write down. Okay, so we write down the metric in the F theory formulation. Okay, but in principle here you could correct the metric, right, because once you have gotten tau, right, you can calculate the energy momentum tensor, right, calculate what the metric will be by solving Einstein's equation. Then that in turn feeds back into tau equation, right, because it's that the metric has now changed, right. So you modify the tau equation and you can keep doing this perturbatively, right, because the small parameter here is the coupling constant, right, which you take to be small, keep as small. Okay, so F theory compactification starts with, as I said, you could do it in general manifolds, okay, not completely general manifolds, I will specify what the condition is, but you could discuss F theory without worrying about supersymmetry. Okay. But our goal will be to again try to preserve some supersymmetry. So we will be starting by describing supersymmetric F theory compactification. Okay, but the generalization should be clear what it means. So it starts with a elliptically fibered. So starting point elliptically fibered, of say complex dimension n. Now what is the meaning of elliptically fibered? Okay. So first of all, the name sounds like it has something to do with ellipse, okay, but it really has something to do with torus, okay, because the reason that it has to do with torus is because the torus is also known as elliptic curve. Okay. Torus is a two-dimensional space, of course, but it's a one-dimensional complex manifold, okay, and often for various reasons torus is called the elliptic curve, okay, and that's where this name comes from. Okay. So it doesn't have anything to do with ellipse that you know of, but it has to do with torus. So elliptically fibered Calabi-Yau manifold is the following, that it is a manifold which has a fiber bundle structure. Has a fiber bundle structure. Whose base B has n minus 1 complex dimension and whose fiber is a torus. Which is one complex manifold. And tau of the torus, okay, this is of course always the structure of a fiber bundle. Tau of the torus varies as a function of z. These are the base coordinates. Is this clear? So total manifold is n dimensional, okay, whose base is some n minus 1 complex dimensional, okay, whose fiber is a torus. Okay, so locally, the manifold looks like some region of the base times a torus. Okay, so that becomes n complex dimensional. Okay. But the torus, the modular parameter of the torus changes as you go from one point of the base to another point of the base. Okay, that is the general structure. That's what is called an elliptically fibered Caravia manifold. Okay, later on we will see how to construct such manifolds. Is the definition clear? Okay. Now, in general, we also allow the fibers to be degenerate. So, allow fibers.
Is the base manifold itself the Caravia?
No, not necessarily. The base manifold is not a Caravia in general.
So together with tau. So
Yeah, so together they are describe a Caravia, but base manifold by itself is not Caravia in general.
It's the fact that together it's Caravia guarantee from the fact that the fiber is a torus, or is it?
No, you can certainly consider elliptical fiber manifolds is not Caravia. Right? So these are the independent conditions that first of all it has to be Caravia. Okay? The Caravia condition is necessary for preserving supersymmetry, as we will see. Okay? Elliptic fibration is necessary for describing an F-theory compactification. If you had another manifold which is elliptically fibered, okay, in this sense, but which is not Caravia, right, you can still consider F-theory compactification, which means that that gives a specific way of compactifying type to be string theory, but it will not be supersymmetric. Okay, so elliptic fibration is necessary for even defining what F-theory compactification means, right? Which of course I have not done so far, right? This is just a mathematical statement. Our starting point is some manifold which is elliptically fibered, which means it has a structure of a base and a fiber that is a torus.
glue these fibers?
Pardon?
How do you glue these fibers? What's the transition?
We'll see. So transition function basically you have to be some on non-trivial overlap, right? Transition function has to be a cell to Z transformation, right? Because you cannot, if you change the torus arbitrarily, right? That's not possible, right? That's a different torus. So that's a singular manifold, right? But what you could do is that as you go from one patch to another patch, right? One torus could be related to the other torus by an SL to Z transformation. Because SL to Z transformation is not changing the torus, right? Okay, it's just re-identifying what you mean by A cycle and what you mean by B cycle. Right? So that certainly is allowed on the overlap.
So it will be a non-trivial. I mean, it won't be trivially fibered if and only if it goes around the singular point.
Well, we'll see. It depends on the structure of the base, right? I mean, if the base is, for example, not simply connected, you could try to get things where you don't need singular points, right? And nevertheless it has non-trivial SL to Z transformation. Right? So we'll see what happens in general. Right? Right now we just think of it as some kind of fiber. Okay? But what I say is we will allow the fibers to degenerate an isolated codimension 2, real codimension 2, to subspaces of B. Okay. So, for example, if B is a two-dimensional sphere, okay, then we allow the fibers to degenerate. Okay. What do we mean we allow the fibers to degenerate? That means that we let tau goes to I infinity or one of its SL to Z images. Because tau is varying as a function of on the base. Okay. Now, as I have already said to the previous answer to in answer to the previous question that it doesn't really make sense, okay, to ask what the value of tau is, right? Because you can always make an SL to Z transformation. Okay? Because torus is described by its intrinsic geometry, right? Tau is the same as A tau plus B over C tau plus D. Okay? So a degenerate fiber, okay, corresponds to either tau goes to I infinity, or it could also correspond to one of its SL to Z images, right? Because it is not to distinguish locally between I infinity and one of the SL to Z images, right? Because that depends on how you have chosen your A and B cycles of the torus. So basically, the torus becomes singular at these points, okay, on these subspaces. Okay. But this does not necessarily mean that the manifold is singular. Okay. It could certainly happen that the original manifold remains perfectly non-singular, okay, even though the fiber degenerates at the isolated points. Okay, and it's not surprising, right? I mean, it's because this basically means that the fibration is not the correct way to choose a coordinate system on the manifold at those points. And if you take, for example, a sphere, right? You can think of a two-dimensional sphere, okay, as circle fibered over a line segment. Okay? But the circle size goes to 0 at the two ends. Right? But that doesn't mean that the sphere itself is singular, right? It's the fibration which has become singular, okay, where the circle size has gone to 0 at the two ends. Okay, so these kinds of behavior, okay, is certainly consistent with the manifold itself being perfectly smooth. Okay, later on we will also deal with singular manifolds, okay, but all I am emphasizing at this stage is that allowing the fibers to degenerate does not necessarily mean that a manifold is singular. Okay, so this is just a mathematical statement, okay, we have not talked about any compactification yet. So now we are going to talk about compactification. So let's consider M theory on M. Okay, so this is T2 fiber over P. Now from this description it should become clear that the information as to how tau varies as a function of the base coordinates, that's an information about the complex structure modulus. Right? That information is contained in the complex structure modulus of the manifold. Right? But it is basically telling us the shape of the manifold. Okay? The size of the torus, on the other hand, is in the Kähler moduli space, right? Because size of the torus, okay, can be changed. Okay, it's basically to take a given complex coordinate system and you change the size of the torus by scaling g appropriately. Okay, now we use the fact that locally we will come to later, that M theory on T2 is equivalent to 2B on S1. Why? Because M theory on S1 is 2A. Right? So M theory on S1 times S1 is 2A on S1, which is equivalent to 2B on S1. If you now follow this duality, okay, you can map the various scalar fields that you get on this side.
Pardon? You needed T duality to go to A from B.
Yes. So M theory on T2, first of all, is 2A on S1. That's the same as 2B on S1. Right? I am calling this S1, but this S1 is not the S1 of the torus. Right? It's some S1. Like, okay, if you want to call it S1 tilde, it's fine. Okay, so distinguish it from any of the S1s which are inside T2. Okay. Now we can work out the relationship between the various parameters. So how many scalars do you have on this side? On this side, the scalars, the M theory in the n dimension, of course, are no scalar. Okay, it has a free form and a metric. Okay. So the scalars on this side are the size of T2 and the complex structure of T2. On this side, it's the size of S1 tilde and tau. This is the axion relator.
Is this tau same as the tau of the complex structure of T2?
Yes, so I am coming to that. Right? On this side, there is no T2. Right? I am just saying that let's just first list the parameters and we will see what the correspondences. Okay, the parameters on this side are size of S1 tilde and tau. Okay, this is geometric. This is what was there in type 2B from in 10 dimensions. Okay? There is no other scalar that you can construct on this side. On this side, because the only form field is 3 form cannot give any scalar on T2. Okay? All the scalars are geometric, the size of T2 and the complex structure of T2. Okay? And now you want to match up the fields here, the scalar fields here to the scalar fields there. Right? And it's obvious how the matching should go, right? Because after all, there is an SL2Z acting on this tau and there is an SL2Z acting on T2, right? There is a geometric SL2Z. So there is no other way than that these two should be identified. Okay. And here, one scalar modulus left from both sides, so they must be the same, right? They must be the same up to functional relation. So these two should be identified up to some functional relation. This we can find out by following the duality chain, right? Because after all, we know how M theory on S1, what the variables of M theory on S1, how they are related to 2A variables. Okay? Then you compactify once more and then follow the relationship between the 2A and 2B variables to figure out how M theory on S1 is related to M theory on T2 is related to type 2B on S1. So this can be figured out. Here, in fact, you don't really have to figure out very much. The maximum that can happen is that this could be a SL2Z transform of this. But that's, of course, you can undo by making an SL2Z transformation on this side, right? Because SL2Z is a duality symmetry of this theory itself. Okay. So this tau can be directly identified as a complex structure of T2. Okay. Here you have to do some work to figure out what the relationship is. Okay. But in fact, even without doing any calculation, we can figure out one thing, which is that if this relationship has to hold, okay, then it better be that when the size of T2 is going to 0, this is going to infinity, and vice versa. Why? Because suppose that there is a regime where this is large and this is large. That will obviously be a contradiction, right? Because the same theory in the same regime of parameter space cannot be both described as M theory on T2 and 2B on S1, right? Because in one regime you will control the number of large dimensions is 2, in the other regime you will control the number of large dimensions is 1. Right? Where number of dimensions could change, right? Number of large dimensions should be an invariant concept, right? Because that's controlled by the spectrum of the theory. Okay? The number of large dimensions better be the same on both sides.
These you can see from duality.
Yeah. So if you follow the duality carefully, right, you will certainly figure out the exact relationship between these two. Yeah, I'll leave it as an exercise to find the exact relation, but I am saying even without doing any calculation, you know that if this duality has to be true at string theory level, okay, it better be that small size here will correspond to large size and vice versa. Okay, but there is a simple power law relation that you can calculate between these two. Okay, so now we are going to use this relationship, but now we apply it on M theory on M. So M is T2 fibered over B. Okay. Now you can imagine a situation where B is large. Okay, and T2 is varying slowly over B. Okay, B you make B large by adjusting appropriate Kähler modulus of the base of M, okay, so that it looks like a large base with T2 varying over that base. Then at any local region on the base, you apply this duality, replace M purely on T2 by 2B on S1 tilde. So now you have a picture that you have a large base, okay, and instead of M purely compactification, you have a 2B compactification, and the fiber is not T2 but it's S1 tilde. Is this clear? Okay. And what is varying? Okay, the variation of the T2 modulus on the base,
Axion delta.
yeah, will now be encoded in the variation of the axion dilator modulus of 2B along the base. Yeah, it will vary exactly in the same way, the way T2 modulus was varying on the base, right? Because you are just replacing, you are applying this duality locally, region by region, right? So whatever was the tau of T2 will now become the axion dilator modulus of 2B.
But sorry, can you repeat this one for?
All this geometric intuition doesn't really, you may question what this geometric intuition means, right? So for this it is useful if the base is large, okay, because so that the T2 is varying slowly, okay, and you can apply duality pretending as if you have only compactified T2 and nothing else, right? That the base is not flat, there is no big curvature along the base direction. So you just apply, you pretend as if it's M theory on T2 times flat space, and compare it with type 2B on S1 tilde times flat space. Okay, this is just for making this identification. Eventually, you will of course not restrict the base to be smaller,
So
large.
if the base is a compact manifold, the size of that should be
Large, yeah. So
So
when you
usually-
start from there, right, that defines a version of 2B compactification in that region, and then of course you can change the moduli and say we will do whatever the 2B does, right, is by definition is a particular 2B compactification.
Is making the base very large equivalent to making the size of T2 small?
No, we are not trying to make size of T2 small right now, right. Making the base very large basically means that you keep the size of T2 fixed, right, and take the base to be large. Okay, it's just to gain this intuitive understanding that when you apply this duality, right, you think of this duality as duality in 10 dimensions, or as a duality valid when all the other dimensions are flat, right? That's the way it is tested, for example, all the BPS spectrum etc. tested in that region, right? So if the base is large, okay, then locally it's as if you have only compactified this T2 and everything else is non-flat, right? And there you know the duality works. Okay, so apply the duality there, okay, and then once you have established this duality at one point, one region of the moduli space, right, then of course it should continue to hold in all regions, right, because you can deform the left hand side theory, you can deform the right hand side theory. Okay, it's just that then the description, okay, is governed by the 2B dynamics, right? You cannot locally again match point by point how tau should vary. Okay. So M theory on M we now replace by 2B on a manifold that is S1 tilde fiber over D. Okay, and Z dependence of T2 modulus corresponds to Z dependence of tau. Okay, how the size of S1 tilde varies is controlled by how the size of T2 varied on this side. Right? The size of T2 goes over to the size of S1 tilde. Okay. The complex structure modulus, which contains information about how T2, the tau, the modular parameter of T2 varied as a function of the base coordinates, that determines the Z dependence of tau. Okay. So in a sense, you are getting a bonus that this gives you a procedure for generating a type 2b string compactification where tau head is as a function of the base. Okay, that's the kind of compactification you are looking for, right? When tau head is as a function of the base, and that's what you get here. Okay, but you are not at F theory yet. Okay, we have one more step to do.
Also, just to confirm the overall the overall manifold.
Yes.
It doesn't have the same dimension across both the sides, right?
Yeah, because M theory is defined in 11 dimensions, this is in 10 dimensions, right? So compact dimensions, this has one more dimension compared to that.
Can you repeat the comment you said about large dimensions?
No, it's just that if the base size is large, right, then locally, even though T2 is varying as a function of the base, right, the variation is slow. Okay, so locally you can think of this as if it's just fixed T2 times flat space time, right, and that's how you understand the duality, right. So M theory on T2 times flat space time, you can replace by type 2b on S1 tilde times flat space time. Right? So in that regime we are sure that the duality should work this way. Right? Once the space time becomes curved, then the relationships also could become complicated. Right? That's why to apply this argument, right, it's easiest, okay, logically it's simpler to see by going to a regime where the base size becomes large.
Yes, no, the statement that comment you made before that, large dimensions should be same.
Oh, here. Well, this is just a statement that if the size of T2 becomes large and this becomes large at the same time,
Yeah.
then there is an obvious contradiction. Okay? There cannot be a duality between a theory, okay, with 11 large dimensions and a theory with 10 large dimensions. Right? This one has 11 large dimensions, right?
Yes.
This has 10 large dimensions. So that certainly cannot be true. Okay, so one more step is needed to go to what we mean by F theory. Okay, and that is the following. Now you take this manifold M, take M, and adjust the scalar modulus such that size of T2 goes to 0 everywhere. Okay? So then on 2b side, the size of S1 tilde will go to infinity everywhere on B. Okay, so S1 tilde now you can think of as a non-compact dimension. Okay. And what you are end up with is a 2b on B with tau z varying as a function of coordinates of B. So this is a compactification in n minus 1 complex animals.
So if I understand it correctly, the whole motive was to give the accent return field to be a function of the internal.
Yes, that's right. Okay, this is one way of generating a configuration, okay, compactification, where axion dilaton fields vary as a function of the internal manifold. Okay. So the general prescription is that you start with a Calabi-Yau n-fold, okay, which is elliptically fibered. Okay. Examine how the T2 modulus is varying as a function of the base manifold, and then simply consider type 2b compactification on a base manifold, on the same base manifold, with tau varying exactly in the same way. Okay. That's the F theory compactification. This of course doesn't specify all the details. You can ask what is the metric on the base and so on. Okay. You can try to infer from the M theory side by starting with the Calabi-Yau n-fold, but the practical method for doing it is that you just solve equations of motion to figure out what the metric on the base is. Okay. But the variation of tau as a function of base coordinates, okay, is implied, is induced from this. Right? That's the information that you gather from this structure.
So base manifold will have each spatial dimension.
It depends on what n is. Okay. So if you start from Calabi-Yau threefold, suppose you have started from a Calabi-Yau threefold, okay, then B will be 2 complex dimensional. Right? So when you compactify 2B on such a manifold, you will get a 6 dimensional theory. Right? Because it's a 2B compactification on 6 complex dimensions. If you want a 4 dimensional theory, if you want 4 non-compact dimensions, you want the base to have dimension 6. Right? So you have to start with a Calabi-Yau 4-fold. Is this clear? If you have an elliptically fibered Calabi-Yau 4-fold, that by this procedure will generate a compactification of 2B on a manifold of dimension 6, which will give you 4 non-compact dimensions.
Calabi-Yau 4-4.
Yes.
So,
So Calabi-Yau 4-fold means,
torus.
yeah, so there is a 2 of the directions are torus, so the base is 3 dimensional, 3 complex dimensional.
One complex.
Torus has 1 complex dimension, right?
Calabi-Yau, okay, 4-4 means okay, 4 complex. Right?
4 complex dimension, right?
Yes.
So from 4 complex dimension you remove 1 because of the torus, right? The base has 3 complex dimensions.
Yes.
That's the dimension of the manifold on which you compactify 2B,
Yes.
right? So 2B will be compactified on a 3 complex dimensional manifold, which is 6 real dimensions. Right? So the number of non-compact dimensions that will remain is 3. 3 plus 1. If the internal manifold is 4 dimensional, right?
So, but shouldn't we always start with Calabi-Yau 3 folds only?
Then you will get only 6 dimensional compactification.
Yeah, but we know the total dimension is 10, so I have Calabi-Yau 3 fold only.
No, that's the point. This procedure is such that you need to start with Calabi-Yau 4-fold to get a 6 dimensional compactification. Okay, because 2 of the dimensions you are losing, right? The torus, you are starting from a Calabi-Yau 4-fold, okay? But those torus directions are not real physical dimensions. Right?
Circle remains, right? One I get remember.
But one circle, that circle you are not sending it to infinity, right? By taking the torus size to 0.
Yes.
So this dimension also becomes non-compact,
Yes, non-compact.
right? So the number of non-compact dimensions becomes 2 plus 1, 2 to begin with and 1 now. Okay. Let's do the counting if it's confusing.
So this S1 is one of the 3 plus 1 dimensions of space.
Yes, exactly. So this S1 tilde will be one of the 3 plus 1 non-compact dimensions. Okay? And the idea is that you will not be able to distinguish once you have gotten this Calabi-Yau compactification, because you really think of this as a compactification on the base B, right, with tau varying as a function of the base. Okay, so let's do this. Okay. So if you start from Calabi-Yau 4-fold, okay, let's see what happens if you start from Calabi-Yau 3-fold. So if you start from Calabi-Yau 3-fold, right? So M theory on Calabi-Yau 3 on CY3. Okay, how many non-compact dimensions do you have? 4 plus 1 non-compact dimensions, right?
RC1 and this injury circle.
No, M theory will not have enough. Right now we are on a compartment of circle. M theory on Calabi-Yau 3-fold. M theory there is no circle. F theory is 11 dimensional theory, you are removing 6.
Yes, yes.
Right? So this is supposed to be the same as 2b on b times s1 tilde. Okay, this is phi s1 tilde phi bar over b, s1 tilde phi bar over b times again 4 plus 1 non-compact dimension. Okay, total dimension adds up to 10. Okay, B has 4 dimensions. Okay, this is threefold, right? So B is two complex dimensions. B has 4 dimensions plus 1 from S1 tilde, that's 5 internal dimensions and 5 non-compact dimensions. Now you take the limit when size of T2 in M theory goes to 0. So which means S1 tilde size goes to infinity. So this S1 tilde, okay, which was being thought of as a compact dimension, now becomes part of non-compact dimension. Right? So it becomes 5 plus 1 non-compact dimension. Okay. So in F theory compactification, starting with a Calabi-Yau threefold gives a theory in which we have 5 plus 1 non-compact dimensions. Because from the 2B viewpoint now, the compact dimensions are only B. There it was S1 tilde 5 over B, S1 tilde has become large. Right? So the only compact manifold that is left over is B. Okay. So even though colloquially one says F theory on a Calabi-Yau threefold, okay, it is really a compactification on 2B on the base of that Calabi-Yau threefold. Okay, the compact space is really the base. Okay. The extra T2 that was there, that is providing the data which tells us how tau varies over the base. Is this clear? Okay. So if we want a 3 plus 1 non-compact dimensional theory, right, that's what we are interested in eventually. Okay. You have to start with F theory on Calabi-Yau fourfold, on an elliptically fibered Calabi-Yau fourfold.
Whose base is CY?
Pardon?
Whose base is?
Whose base is 3 complex dimensions, right? If you have a Calabi-Yau fourfold which is elliptically fibered, its base is 3 complex dimensions, which is not necessarily Calabi-Yau. Okay? But that's what F theory compactification will give you. Okay? It will give you a 2B compactification on the base, okay, with tau varying over the base. Okay? How tau varies over the base is encoded in the original Calabi-Yau manifold.
So you take M theory on CY4, then you have 2 plus 1 non-compact dimensions to start with.
Yes.
Then the same thing goes on.
Exactly, that's right. Okay, but while discussing F theory compactification, you don't have to go via the same theory route. Right? Once you know the picture, right? What you will say that you take an elliptically fibered Calabi-Yau n-fold, okay, identify its base, okay, and consider 2B compactified on that base, okay, and the information that you capture from the original Calabi-Yau n-fold is how tau varies over the base. Okay? So you think of this as 2B compactification on the base, and you learn how tau should vary over the base from the information from N. Okay. Now this is also good because if say M theory on Calabi-Yau fourfold, how many supersymmetries will it have? Okay. It will break the supersymmetry to 1/8 its original value, right? Because 1/8, let's say. So Calabi-Yau threefold breaks it into 1/4, right? From 32 it comes down to 4. Sorry, it comes down to 8, right? Calabi-Yau threefold. Calabi-Yau fourfold will break it to 1/8 its original value. Right? So from 32 it comes down to 4. Right? And that's what we really need. Okay? So this procedure, if you start from what you colloquially say F theory on Calabi-Yau fourfold, okay, imagine in some 12 dimensional theory compactified on Calabi-Yau fourfold, but this is really a 2B compactification on the base of the Calabi-Yau fourfold. Okay. This gives you a way to get supersymmetric compactification on 2B with only n equal to 1 supersymmetry. So Orient-fold was one way, you could get n equal to 1. F theory we see is another way by which you can get n equal to 1 supersymmetry on starting from type 2. So next time we'll see that these two are in fact as different ways of describing the same string compactification. Okay, so I'll stop here. So next class will be in the next week.